Okay, I'm going to now, I've given you some background on wood as a material, some background on some of the things we see, the importance of wood and moisture interactions. The next phase of this presentation, we're going to look at some example evaluations. All of these are covered in the Wood and Timber Condition Assessment Manual in much more detail. I'm going to try to get through some work we did on the oldest commissioned ship in the U.S. Navy, Old Ironsides. It has some very unique characteristics. A school gymnasium with some barrel arches, trestle, which used to be the largest glued laminated structure in the world, and timber bridges. But before I start on that, are there any questions? And if so, feel free to type them in, and the folks at the Wood Council will accumulate them, and we'll try to answer them at the end. Is that fair, Marcy?
Yeah, Bob, we could probably jump in just with one or two here right now. So before we do that, though, we've got a lot of sharp participants here, and when you were talking earlier about eye joists, you mentioned notching or drilling holes in the flange, and a lot of those folks piped up, kind of lit up our Q&A window there and said that they are pretty sure you meant the web of the eye joist is where those holes and notches.
Oh, definitely. I apologize. Yeah, the prefabricated punch-outs are on the webs.
Yeah. So just want to make sure we cleared that up. That lit it up. So I want to make sure everybody knew.
That's exactly right. The problem is cutting off the flanges.
Right. So
I apologize. Talked so many times. Yeah.
Nope, no worries. The other one goes back to sampling, and I think there's two different sample sizes that you might need. If you're just doing species identification, somebody said, I sent in a sample as small as a toothpick. Is that big enough for species identification? Then I think if you could talk about that and then talk about what sample size you need for physical testing, maybe that would be helpful.
So that's great. I'm assuming everybody heard Buddy's question, so I won't repeat them. Toothpick size is pretty small. I wouldn't go there. There's, in the Wood and Timber Condition Assessment Manual, I'm going to pull that up right now to that chapter. We wrote a whole manual on wood sampling for wood, and I'm going to look that up. I would say if you could come in with somewhere around a a 1x1 sample, you'd be fine. I'd say an increment core size sample would be fine. Let me see. That would be fine. Now, having said that, there are some folks that would tell you they could probably do it with a toothpick, but most of the folks are doing it. Think of a hand lens that is very small and a 10 power lens, and holding that piece up. So if you could just notch out or take a piece out, maybe a 1/2 inch by 1/2 inch even, you'd be fine. So you don't need a big section. Be careful where you take it from. Obviously, we don't want to take it on the tension side of any members that are in bending or any tension members. We don't want to do that. So hopefully that answers the question. Now, there are some people in a real bind would tell you they can do it with sawdust. I'm not convinced of that, and I would not recommend that, but there are some people who would tell you they could. I recommend something in the neighborhood of 1/2 inch by 1/2 inch or an increment core. If you're doing heavy timber construction, they can get them from an increment core. What was the other one, Buddy? I forgot.
Well, if you got to do physical testing, what length would you need?
Okay, maybe some cross-sectional. Yeah, that's a good question. You can do physical testing. Depends on what kind of properties you want. Most of the small clear testing we do, or anybody does, are controlled by ASTM standards. And the normal ones we talk about, ASTM DES140, I think, Buddy, I can't remember. But most of the small clear stuff, if you want to do, bending tests on a small clear specimen, they're basically, what are they, Buddy? 3/4 by 1.5 inches by about 6-8 inches long. So you don't need a piece. So they're in that ballpark. Now, people can do, in a lot of these test labs can test smaller specimens, but it depends on the property you want. But what I would defer to, it would be the ASTM D series for the Committee on Wood and look at those, because that's usually what we're going to fall back on.
Yeah, I think D245 is probably the one you're thinking about for...
Not 198. 198 is the full size.
Yeah, so, okay. One other question, then I'll let you keep on going so we don't run out of time.
Any other questions?
Yeah, they're wanting ballpark costs on the resistance drilling devices. Any ballpark estimates on that?
Ballpark estimates on that. It depends for the drilling resistance things, and I just came back from a meeting on this, and somewhere in the neighborhood of, a couple $1,000s up to $10,000. That's what I heard. Now, we have not purchased one in a while. A lot of that depends on what kind of bells and whistles you want on it, whether you want, to download it to your laptop, or whether you go with, hard copy or some combination. They're constantly evolving on those things. The concept hasn't changed, but the evolution has led to more and more ease of interpretation. So I'd say somewhere between $2,000–3,000 up to $10,000. That's just a round number.
All right, all right.
The websites and the contact information is in the chapter on the Wood and Timber Condition Manual. I'd recommend get on those websites and get a quote from them.
All right, sounds good. Well, I'm going to let you keep going so we don't run out of time for you to go through some of these case studies, and we'll pick up more of those questions at the end if we have time. Okay,
photos and everything are good, buddy? Everything's good?
Yep, good to go.
Okay, the first one I want to talk about, thank you guys for the great questions. Thanks for catching me on that I-joist one. Thank you. I've just done too many of these. Anyway, the first really inspection I want to talk with you about, it's not a building per se, but it is a very unique wooden structure. It's Old Ironsides, USS Constitution, and I want to highlight that because there's some unique things in there, and it highlights some of the things we've talked about in the prior part of this discussion. That's a picture of Old Ironsides after her dry dock in the late 1990s. It's a very interesting ship. It was commissioned by President George Washington, and construction started on it, just some interesting facts, in 1794. It actually cost, and I got these numbers off the historic site, down to the penny, $302,000, $302,718.84. I'm not convinced we have our budget quite that tight anymore in the federal government. About 200 foot long. When it was sailing, we had a crew of 400 on it, never defeated in battle. It's still a part of the United States Navy. It's the oldest commissioned ship in the world. We have about 1 million visitors, plus or minus, that go through that ship from all over the world. I want to tell you that we got called into it as a federal laboratory and as the nation's wood research laboratory. We've been involved with it and the inspection of it numerous times. I was fortunate enough to be in here when they did it for the dry dock just prior to the anniversary of its 200th anniversary. And in that particular case, we went through the ship, and I just want to share with you some of the unique characteristics of it. It's all wooden, above waterline, below waterline. And what you'll see in this photograph, it's from a very unique species of wood, and that's where we go to the species identification part. That is, quote unquote, a live oak tree. It's not just alive, but the species is Quercus. I forget the species name, but that's the genus name. But the common name is, quote, live oak. It's very dense. It grows in a very spreading format like that. It has some very unique characteristics of it. It is very strong. It's very, very decay resistant, and it is very, very resistant to impact loads. But it grows in a sprawling type of tree like that. It doesn't grow straight up. It doesn't have a straight bole like we do in the others. So what I want to point out to you is how important that is in the design of it. The ship itself, if you look back at that tree, you'll see various branches that go out. The neat thing about that is when a tree forms branches like that, the fibers actually flow along that curvature. So it's not like when we connect things together and we put two pieces together and put a plate on it. They actually flow there, so they're very strong that way. The folks, when they built that ship, took advantage of that, and they used every piece of every one of those trees they could get. And here's just an example of what they did. They had some straight sections that they used for various straight sections, but they used knees for braces. They used some of the bowed areas for braces. I'll show you some pictures of that. But very, very unique, great understanding of wood as a material, and did just a fantastic job at utilization of that material. Very, very unique. I got to tell you, too, that what was unique about this was that it was, at that time, our secret weapon, because this species of wood only grows in the southeastern part of the United States. It doesn't grow up north here. It doesn't grow in the west. So it was kind of the secret material that they used. This is just a model of the ship. It's multi-layered. All wood construction held together by copper and metal drift pins. This is a example. When we were asked to do the inspection, the first thing we did is we made a mock-up of the hull. This is a mock-up, actual full-size mock-up of the hull of Old Ironsides. What I want to show you is that it's a cross-laminate construction that is solid oak, just under 2 foot thick. So in the outer laminations, the ones facing us in a horizontal direction, most of the fibers were in the direction of the member. In the rib members, they were perpendicular, and in the back side of that, they had another layer that was like the front layer, all solid oak, 2 foot thick. The pins there were copper. If you can imagine, they didn't have electrical power tools there or pneumatics. Everything was either by hand or water driven. All those were drilled and pounded by hand into the ship. What I want to tell you too is that the siding of this, because of the structure of the wood, the density of it, the durability of it, it has remained floating for over 200 years. But because of that construction technique, it really was good at repelling cannonballs. It absorbed energy, dissipated it, and would flex a little bit, but it really is a very, very good material for that application. We were called in because there were a couple things that were going on. In the ship itself, we had hogging going on, which is before and after the ship were actually drooping, and as a consequence, the keel was becoming elevated, and we noticed that was happening over a period of time. This ship has its own budget line item in the federal budget, so this is a very important history of the United States. We were given the mission that this thing has to float forever, and in addition to fixing and repairing these kinds of things, we had to make sure that we preserved as much of the original materials. Just for your knowledge, if you ever wanted to look it up, there was an article written on what we did in the July 1996 version of National Geographic. The inspection techniques we used, visual and including photographs. We used some photographs that went back quite a way. We used ultrasound techniques. We used some radiography, did some chemical tests, and then some mechanical tests on the ship. Just a little bit here, we want to tell you that one of the problems that contributed to that hogging was the copper pins. It's estimated there was about 50 tons of copper pins used below the water line of the ship to hold that thing together, and there was an equal amount of iron pins above water line, so a total of about 100 tons of pins. Ironically, all the material below the water line, or in essence, all the material below water line is original, and a lot of those original pins came out of Paul Revere's shop, and you could see his logo stamped on the head of those pins. Anyway, one thing we saw was we used some ultrasound and X-ray techniques to look at the actual characteristics of the pins, and we saw some deterioration of the pins. No decay in the wood, but we did see some metal thickness around them. In addition to that, we saw, when we brought her to dry dock, we did start to see some deterioration, and we did run some mechanical tests on some other material we had of the same species that had been preserved, and some from the ship. And we noticed, we did some compression tests with the fasteners, and we did notice a significant drop-off, not in the strength, but in the stiffness of those joints. And we attributed that to the cause of the hogging in the ship. This is just a photograph of her. You can see her just outside. This is the dry docking prior to her going in. Now, what I want to tell you, and this goes back to the wood-air interaction kind of thing, the only place we found decay, most of the places we found decay in the ship, were right at or just below or above the waterline. And what we saw was below waterline, no real deterioration, all original material. And why? There's water there and there's wood there, but there's no oxygen. Above waterline and above that zone, the moisture content was low, so you didn't have that. Right at that waterline, above and beyond, above and below that just a little bit is where we saw deterioration. We were able to map that out, and we were able to determine which pieces had to be removed and had to be replaced. The other thing that was very interesting on, and I wanted to share with you, is that in this particular case, because of its historical significance, we did everything we could to put the same species of wood back in it. Ironically, when George Washington commissioned this ship and dedicated it, he planted live oak trees, seedlings, on his plantation. And it's documented that he made the statement, as a lot of our politicians do, that some good things are going to happen, and he said that the wood from these trees will be used in 200 years from now in the repair of this ship. Well, those trees were actually came down in a hurricane about 25 years ago. They were taken, they were preserved, and they were put in a pond, and they were kept. And those trees, the wood from those trees was actually used in the repair of the ship. The Forest Service, my bosses, actually went back and planted the next generation of live oak trees for the next 200 year out. So it's a really good story about wood, engineering, understanding about wood, durability, and also about the sustainability and what we can do with wood as a sustainable engineering material. Next one I want to touch base on is the school gymnasium, and these I'm just going to quickly go through, but I apologize for the quality. These are older slides, but they really highlight some unique things. These are older gymnasiums that were built in the 70s, some of the first glued laminated timber arches that were built, and the main support structure, this was in Rathdrum, Idaho, were laminated barrel arches. They were laminated Douglas fir. The problem area was at the arch ends that was exposed to weather and rested on a concrete foundation. You can see it there on the right-hand side. It had some very heavy painting on it, lead-based, ironically, but it was not allowed to dry out. As a consequence, there was some indication of decay because there was a lot of cracking and peeling of the paint. So the inspection was, the goal here was, again, to go back what we talked about, looking for moisture things and then doing your inspection based on that. Looking at where wood, water, other materials interact, and then looking for decay in that areas. And what they did is they used, here's a close-up of it, we had wood, steel, fasteners, and concrete. And what we found was, again, a perfect place. These are untreated members, so there was no preservative in there. The water would migrate up the specimen, perfect place for decay to happen. Used a variety of techniques, and especially stress wave techniques, and because at that time the probing or resistance drilling was not that far along. But this is what I'll show you from one of those older reports, and it's in detail in the one chapter in the condition assessment manual. But very similar to what you see on a tooth decay problem. That's the side view of a schematic of one of those arches, and the numbers on there are indicative of the time it took the wave to go through. We started near the end and worked our way out, and you can see that dashed line represents where we found decay and deterioration based on stress wave times. And basically, we knew what good sound wood would be, those lower numbers, and we knew when we hit decay because of deterioration how bad those numbers or how much those numbers would change, and as a consequence we could map out where the decay was and make appropriate repair recommendations. So worked out really well. What I'd recommend today for something like this in what we do is when we get a map like this, we always follow up with some kind of drilling, coring, or micro-resistance drilling to verify our findings and just make a complete package. But really one of the first works done on a very nice piece of technology and a very nice piece of science. Trestle. I want to show you a picture of trestle. It's one of the largest structures in the world. I don't know if it's the largest anymore, buddy. You can correct me. Here's what it looks like. That is an actual B-52 that was on the structure. It's located in the New Mexico desert, very arid. It was constructed between 76 and 79. It was a test stand for aircraft, and it was composed almost entirely of wood. Even the pins in there were wood composites. And the platform was about 200 foot square, and it had a height of 118 feet. So one of my good friends and colleagues, Don Neal, was asked to go out and do a condition assessment on it. Of all the members there, he tested just about 5% of the total. That it was just shy of 500 total Blue Lamb members. Now, what he did is went through there using visual techniques as well as some of our ultrasound techniques, parallel, perpendicular to the grain, to look for decay. Now, I can tell you that it's in a very arid environment. In essence, they found no signs of decay and no deterioration from decay. So that was good. But in addition to that, they showed a slight deterioration in the decks, and they recommended some replacement of the decking material. What they also recommended was, if they did that, it would be okay to increase the design loads to accommodate ultimate aircraft. So very important, but very intensive, very, very well done, well documented. It's in the condition assessment manual, and the key is there. If you really want to get into it, it's one of the very first assessments where they took some of those NDE technologies and actually used them to derive allowables or more allowable design values. It's an excellent example. I recommend it highly. It's a great paper, and it's available in the manual. Okay, I'm going to now go to Tim.